Great.
Okay. And we'll start again.
Yes, interestingly, so when we first tried it with Stefan, everything worked right away, and now that's how it goes. Yeah, it's very, very strange. Okay, so sound works. Okay, so just some background for this talk. So I guess you might also have heard in the news that there has been some big advancements in deep learning in the past years. Since about 2010, there were some great advances, especially in speech recognition and image classification using deep learning. And I think by 2016, Microsoft announced that now speech recognition has reached the level of human capabilities, and I guess after that it's been only getting better. So now computers can understand speech better than us. And the same with image classification. They are very, very good at figuring out what's happening in an image. And then some years later, Google introduced the WaveNet architecture. It's actually here. That's their animation, how they advertise. So this is a so-called end-to-end neural network that takes the input signals and in these stages, layers, it produces the output signals and then uses that information also to produce more outputs. And this is a kind of feed-forward network that works only solely in the time domain. So it just produces one sample after the other. There's no pre-processing or feature extraction, which used to be typical for machine learning back in the day or before this. And they used this for speech synthesis, but they also showed some music synthesis examples at the same time. So it could already play the piano and also do random music and other things. And also in 2020, Google's Magenta project introduced something like a concept called differentiable DSP, or differentiable digital signal processing, which also combines like some other previous ideas from traditional signal processing and machine learning. So these are some things that have happened and kind of were important also for audio people. So I first gave this version of this talk at the DAFX conference, Digital Audio Effects conference, a while ago, and so I for this presentation I checked what had been happening in that conference, because it's an audio conference. So it turns out that the first paper on deep learning in that conference series happened here in Edinburgh in 2017. It was just this one paper that was related to the parameter estimation of physical models. And then the year after that there were already 9 papers. So for example, this one paper by Marco Martinez and Josh Wright's end-to-end equalization with convolutional neural networks, which kind of already hinted that we might be able to learn, like with machine learning, some audio processing techniques automatically. It didn't do it yet, but soon after that things started happening. And then in 2019 there were over 10 papers also in 2020, and it actually got quickly hard to count how many papers there are. Many people and papers mention deep learning, but they actually don't do it, or they do it. So you have to actually read through all the papers afterwards. At that conference a couple of months ago, we had 2 sessions on deep learning and also several other deep learning papers. Also some other kind of shallow machine learning papers, so not deep neural networks, but smaller ones. But not all papers were related and have not been related to deep learning in these audio conferences. And I would say, fortunately, because I think it's not great if we forget about all the history of signal processing and all that. But of course, it's clear that machine learning is now here to stay, and deep learning also. So next I'll tell you about the beginning of what we did with my colleagues and students first. So in 2019 we published this paper, Deep Learning for Tube Amplifier Modeling. This was also presented in the UK, in Brighton, where they had the big IEEE ICASP conference that year. And so what we proposed here is a WaveNet-like structure, which has these convolutional layers, neural network layers, and and a post-processing module that collects outputs of all those layers and then produces like the output signal. And it also has a conditioning, so kind of user controls. The amplifier that we modeled had a gain control that affected the sound, so that was also included as a control. So basically it learned the sound of the timbre of the tube amplifier also with any settings of the knobs it had. And so this was heavily inspired by the WaveNet architecture. And here are some results. This is just the waveform of the example waveform where the blue curve is the reference signal, so like how it should be, and the red one is the output of the WaveNet, larger of the WaveNet structures we tested, and at least here it looks like a perfect match. It's not actually that, it's not really perfect if you macroscopically look at it, but it was surprisingly good, and we were surprised especially of the fact that phases are also okay, so it truly does exactly the same as the amplifier it was modeling. Actually, we thought we shouldn't be so, it wouldn't have to be so accurate, but we didn't actually figure out how to make it blind to the phase, so it just did what it did there. And here's also some examples of or results from a listening test where we played. We had the reference signal, which was the distorted guitar sound that we tried to emulate, and then we had two different versions of the WaveNet. We had the bigger one had some 30,000 parameters, the smaller one just a few hundred, and then we tested it against or compared it with the kind of old-fashioned multi-layer perceptron, which is kind of like a neural network from the last millennium, and then the best so-called black box model from the past few years, which we call the block-based model. And the anchor was which basically was there just to show the audience or demonstrate how bad things can be. So it was maybe like a hard clipper and a low pass filter or something like this. It sounded distorted, but in a very, very, very simplified manner. And so these are the results that people gave for the bass and guitar, electric bass and electric guitar sounds. You can see, and these are the mean the blue. The black dots are the mean values, and then there's the confidence interval. And we can see that the WaveNets are clearly better than the other models, but they are still quite far from the reference. So people liked them, but still found a difference between the real thing and the deep neural networks. Then, actually, at this point, also Alec Wright moved to Finland and started helping us. So we next went to use recurrent neural networks. So recurrent neural networks are networks where you have feedback in the system. So there's these states inside the system which kind of hold the intermediate values of computing, and they are used in the next rounds when the neural network does its job and predicts the next output samples. And these are updated all the time, but these are not like circuit states. So these are not, although we are modeling an amplifier or a FX box or something like that, these states should not be confused with what happens in the real thing. These are just abstract states of the system, and usually we don't understand what it's thinking and what's happening there, but they are just numbers, or matrices of numbers. So we in these kind of recurrent neural networks, there's two different types of common units that are used here as a recurrent, as the recurrent unit, which is the main kind of computing cell. So there are gated recurrent units and long short-term memory units. Short-term memory units are kind of a little bit more complex way of learning dependencies in data. They have 4 different kinds of gates, how to decide what to remember and what to forget. A gated recurrent unit, so we have 2 different types of gates, so it's a kind of simpler and faster way of computing things. So what we did, we basically had guitar sounds and pure like dry guitar sounds, and they were also played through an amplifier, actually amplifier model, like a SPICE model, like a very accurate circuit model of of the amps, and we were modeling, and then we gave to the neural network the dry input audio and also the target audio, so how it should sound when it's distorted, and these are like paired data, so we always knew the input and output very accurately. And then these data would be fed, the raw audio would, or dry audio would be fed into the neural network, and then it would predict some output, and we would then compare it with the target audio. And of course, first it would be completely wrong, nothing good there, but we would use a loss function to compare these, so it's kind of an error measure how wrong it is, and that information was then used to train the parameters of the neural network, so that next time it would be a little bit better. And when you repeat this thousands and thousands of times, then it learns what if the circuit, if the machine learning and neural network structure is capable of doing it, it will learn it. So we updated the parameters every 1,000 samples. For example, in this case, we used so-called truncated backpropagation through time system. And we had different numbers of units, 19 to 60, 16 to 96 recurrent units in these networks that we tested. Another trick that was used already in our early works was a pre-emphasis filtering. So the idea is that when you compare the network output and the target output, you can feed them through a filter. So this is just a kind of, this here would be some sort of high pass filter. So the idea is here that we can emphasize those areas in frequency that might be more important or relevant for human listeners to hear, for example, differences in the sound. And only then the signal would go to the loss function. So this is one way to guide the neural network to learn its job better where we want it to. And we already used a high-pass filter like that in the first tests back in 2019. And then with ALEC, we actually figured out that there might be a better way of doing it, and this is the A weighting pre-emphasis that we developed. So this is based on the A weighting, which is used like in loudness and noise measurements. So basically it's imitating the way hearing works. So we are most, let's say, the ear is, or the hearing mechanism is most sensitive to these mid frequencies between about 1 to 3 kilohertz. So it makes sense to a little bit boost those. And then there's a lot of okay, we are not so sensitive to low frequencies anyway, so it's good to suppress that. And then at very high frequencies, there's not much audio data even in those guitar amplifier sounds, so it felt like it's a good idea to suppress them a little bit, especially closer to 20 kilohertz. There's nothing to hear, nothing to be heard, and not much data either. Oh, by the way, there's some QR codes here, and so this, for example, I think takes you to that paper. So if you wanna, you can also find that paper. And because of the shape of this successful filter, we actually started calling it the whale, and we always want to print it with the blue ink in these papers and slides. So here's what it does. So we have 3 curves here. The red one is the error curve without weighting, and the black one is with a high pass weighting, and the blue is the whale weighting. So, and we can see that where it gets better is here in the middle frequencies. Where's my mouse? There. So this is where we can get a little bit smaller error with the weighting in use other than in these other cases. And here's a few sounds I could play for you. So this is the target sound again. And when you use the weighting or loss function with the neural network, it sounds like this. Often people would say that they are almost identical, and I didn't hear a difference from here, actually, at least. And so we also made some listening tests and checked that indeed the whale sounded always a little bit better for people, but just a little. With larger models we get more benefit, and indeed here in this case we get a statistically meaningful difference between no weighting and the whale weighting. And the great thing here is that this is a free lunch in the sense that you use this filter when you train the network, but afterwards there's nothing left of it. It only is used during training, and it doesn't make the like the neural network any more complicated than it is. So it's in a sense really a nice technique in that sense. And of course it makes sense to use it. It even doesn't make the training slower really, because it's quite heavy anyway, so that little filter doesn't make a big difference there. Yeah, another nice thing which we learned quite early is that not so much data is needed to train neural networks to learn guitar distortion. So we found that indeed only 3 minutes of data is okay. So we can see that here that when we tried more adding the number of or the amount of data to several more minutes, it kind of saturates, and we really don't get any better with 4 or 5 minutes and even longer. I think first we used something like 4 hours of data, but we soon realized that oops, well, we don't need that, so maybe we shouldn't. And that's actually quite different from some other cases, like for example in image processing, where they might use like huge numbers of data, and also the training might take weeks or months. These usually take just some hours or days, and the amount of data is also quite reasonable. Actually, if you really look close, you might find that even after using just 30 seconds or a minute is already quite close to the optimum. But of course it doesn't cost much, so of course we would use at least 3 minutes for this in this case. And so in 2020 we also already noticed that we can also run these models in real time with the computers of those days, and that was an Apple iMac machine that I think Alec was using at the time, and we found these are the last line here are the speeds. This is like times real time, so how many times you could run that system in that computer. So 8 of those models, or 4 of those models, or 2 of those models. And so the best model we had was already running. We could run 2 or 2.5 of those models in real time. Of course, maybe that's not enough really, because in practice, of course, people would use also the same laptop for many other things. They would have a reverb there and many compressors and maybe software synthesizers and things like that. But at least it showed that it's possible. Of course, now again, computers are faster, and there's also some tricks to make the models a little bit smaller. So that's how it was back then. And these the error numbers here, these are just I believe squared errors, error to signal ratios. These are quite small, but indeed these numbers usually we found out don't mean much, because it's really important to have listening tests and see hear what people think about them. Sometimes the error could be somewhere that you don't really hear it, and it gets a little bit larger. Still, it sounds great. Sometimes the error is just where it really hurts, and then even a small error here actually makes it sound a little bit bad. But anyway, around that time we found out that now we could actually make kind of deep fake models of some amplifiers like this one, the Mesa Boogie 550. So when we compared those different techniques, including our RNN and then a big wavenet, we found that now the confidence intervals of the models we did and the reference actually were overlapping. So at this point we found out, looked at each other with Alec and thought, wow, that's something. Now we did it. So it's kind of the big thing that we could actually fool listeners. and they could not anymore see or hear which one is which. We can hear the example of this model. This is the target sound. Here's the neural network, which is very similar. It actually turns out that in some of those signals we released, there's also some hum in the original sounds, and somebody actually then said that they noticed the difference because the other one had hum and the model didn't have. Of course, we could have also included some hum in the neural network models, but we never did. And I think users probably wouldn't like them. If you can get rid of the hum, I think you would. I would say. Anyway, at that time we also made a press release, and we got to news with Alec. So we made this headline: "Deep learning AI can imitate the distortion effects of iconic guitar gods." And this was the first news by Digital Trends. And they actually also interviewed us. They didn't only copy the press release. All the others, they just copied the same text all the time. And there's Alec playing the guitar in his lab coat and the anechoic chamber. Finally, we also got to the Finnish news, the Helsinki news, and we were very, very proud. People didn't ask for our signatures, however, but anyway, it was a big moment. And anyway, after that, I also felt that it was actually a big moment, and that year 2020 really made a difference in deep learning and machine learning in audio. And I would now say that if somebody asks, like, when did this era of machine learning or deep learning in audio start, I would say 2020, and partly because of this. There's also other reasons, but. So here's my slide that I now had to update. I always show this to my students on the introductory lecture. So I'm dividing the 100 years of audio history into like these different eras. So first there's the era of electroacoustics, like the golden age of radio, when we already had loudspeakers, microphones, amps, and so on, and the movies already had the soundtrack and so on. Then some 20 years later, transistors and diodes started replacing tubes, and audio electronics started shrinking. There were transistor radios and things. And then in the 80s, we entered the digital audio era when the CD player was introduced, and the first digital synthesizers, and a little bit later also the MP3 and all that. And then in the 90s, approximately, we started this kind of virtual audio technology. We started modeling many different things, and had started to have multi-channel sound, to have more immersive experiences, and all that. But of course, we're still doing it, but it was a new thing back then. And Yamaha introduced another new synthesizer, which was a physical modeling synthesizer for the first time. But then after that, so now I added this new section here, so deep learning for audio in 2020, and so it's characterized by deep neural networks, big data, DDSP, and diffusion models. Diffusion models are another new like generative deep learning technique. And then there's some of these characteristic products. Neural DSP, a Helsinki-based company who actually hired some of my students. They introduced the quad cortex system, like a hardware product that models amplifiers, and then also Native Instruments introduced the Guitar Rig 6, which has also circuit models and machine learning models for guitar amplifiers. And for example, the SoundStream codec, which is a neural audio codec, was introduced. So I think that's a good point if I had to choose one moment. And of course, for us it was because that was the first time when we could fool listeners with the deep neural network. All right. Next, I would talk about something else. So what we did after, what we have been doing after guitar amplifier models. So recently we have been doing lots of audio enhancement, for example, denoising of old musical recordings from history. So here we often use a pre-processing technique. So we actually don't feed in just pure audio, but we do spectrogram. So we do frequency domain processing, so we show spectrograms to the neural network, and it all becomes a little bit more like image processing actually. So sound becomes like a colorful image for the neural network. Here also we use the supervised learning technique, so basically show pairs of corrupted and clean audio to the network so it can compare and learn the properties. And in this case, in this first study, we had 40 hours of clean classical music, 2 hours of noise. And that was actually a tricky thing to have. So what we tried to clean old gramophone recordings, and there's actually not really noise published anywhere. So my student who was doing this, he had to actually first program a machine learning technique to try to figure out where's noise, just noise, no music, but only noise in gramophone recordings. And it turns out that in the beginnings and ends of songs, you can have it. So there's lots of digitized gramophone music available online because it's kind of worthless nowadays. Nobody buys them. They sound so horrible. They just give it away. But so it was great stuff for us. And here are some of the noises that my student extracted. So these are just gramophone background noises without music. Here's another one. Yeah, so he collected 1,386 of these little segments, and we actually then put them together with clean, modern classical music. So we added these noises to them, then made these pictures of spectrum pictures and showed them to the network. Then we also, when the neural network computed the output spectrogram, we went back to the time domain and we compared the original music, clean music, with the output of the network, and then adjusted the network to make it better and better every iteration. So that was the logic how we did that finally. And this was presented in 2022 in a conference in Singapore. So this is how it works approximately. So we used UNet architecture. So UNet is this type of machine learning technique or neural network architecture that does a dimension reduction. So it goes from original dimension to a lower one and then goes up. So it kind of makes a U like that, and I think that's why it's called a UNet. It was originally used for medical imaging, like capturing some patterns in medical images. But now it's used for capturing patterns in spectrograms of music. And we actually had to use 2 UNet stages. We figured out that if you only used one of them, it left some noises which were quite annoying. So it was much better than the original, but not good enough. And my student is a perfectionist, so he wanted to do better. And so he figured out that you could actually use a second stage. And so basically we pass from the first neural network some parameters to the second stage. There's a module called supervised attention module, or SAM here, that actually selects what are the best things that the first stage learned and gives them to the second stage, which then handles the rest. And finally here we also we compare like the output of the second stage and the first stage to the original clean music. So actually we are training both at the same time finally. And when they have learned, then the quality is actually pretty good. Here's some examples. So yeah, and also in this case we tested it with synthetic examples, so we added those short examples of noises, but then we also tried it with real gramophone recordings because they are available. And of course the big thing is, can you actually improve the real recordings? The synthetic stuff is kind of, why would you do it? Because you also have the clean recording. But this of course is interesting to do. And it turns out, yes, it can do it. And very surprisingly, everything goes away instantly. I also tried this with another student over 10 years ago, and back then, for example, we had to detect all the clicks in music and find a way how to extract them one by one, not spoiling the music, and how to subtract the background noise without spoiling the music and without these little birdies appearing, which also always seems to be a problem, like in low bandwidth MP3s, for example. But nothing of that happened now, and everything just goes away. And I'll show you. So this is an example. Here's Enrico Caruso singing a very famous song in where is my mouse actually? My mouse seems to be, how can I play anything if I can't see my mouse actually?
Keep dragging it to the left. Other way.
Yeah, there it is. Okay, good, thank you. Yeah, so you get an idea how bad the quality is. For modern people, that's not something you would buy. So that we have to do this thing. So this is the denoised version. So actually, everything really goes away. No clicks, no noise. And the great thing with this is that we can also compare easily these original and the denoised version, because the neural network does all the cleaning kind of in place. We don't touch the phase at all. So we can actually subtract the two signals and see what's left. So did we take away too much of the music, for example, or what? Actually, that would be a bad thing if we still hear the music in the subtracted signal. But let's see what we have. So here it is. This is the residual of these signals, difference of these two signals. Did you recognize the song? I hope not. Yeah, so there's no music, so that's good. So basically this means that the deep learning network learned to separate music and noise from each other, and it actually carves away all the clicks and noises, but doesn't touch the music at all in this case. So that was good. However, it also revealed another problem. Maybe you can see this in the spectrogram here. It has this black sky here, which somehow does look strange. But this basically means there's nothing at high frequencies in this music recording. And that's a typical thing also in old gramophone recordings. Because of the recording technique, high frequencies could not be recorded. So everything stops at about 3 or 4 kilohertz, and that's it. So basically trying to sell these again or play these to like modern audiences, I think might be again hard, because it still sounds a little bit strange. So that was the next thing we started actually solving afterwards. And that's when my student Eloy Moliner, he actually started working with and testing with so-called diffusion models. So diffusion models were first also introduced for image processing, and the idea here is that you kind of learn this type of diffusion process, which is the same idea as if you have a glass of water and you pour some color or ink in it, and you see how that color kind of spreads to the areas where there's not less concentration of the color, and it diffuses and finally kind of fills the whole and colors the whole glass. And the idea is that we do we learn to reverse this process. We learn how it happens and how we can go backwards. So we do reverse diffusion, and that's what they also did in image processing. And the great thing here is that if the neural network can learn how this happens, from how the diffusion happens, and it also has a good understanding of the statistics of these clean samples, so clean glasses of materials. It actually always goes back to a realistic version of the original data. So for example, if there's an issue with the image, it goes noisy and goes back, and the problems are gone, because it only reconstructs a version of the clean class that is good, so not without errors or mistakes. And the same for audio. So this is really good for solving so-called inverse problems, where you estimate data that is not there. Declipping is a typical example. So this is a declipped or clipped signal here. So we have clipped it at levels or sample values -1 and 1. So the original signal might have gone higher and lower than that, but now it's just hard clipped like that. And now if your task would be to reconstruct the original signal, there's not much information to use, because you can't figure out how high or how low those peaks might have gone, because there's only a constant at that moment. But now if the neural network has seen many of these audio signals and it recognizes from left parts, and that's called declipping. And we were interested in doing bandwidth extension, which is pretty much the same idea. And here's an example. So this is a method called BABE2, blind artificial bandwidth extension. Sometimes it's hard to find good names for methods, but we just thought, what do we call this? Blind artificial bandwidth extension sounds kind of complicated. Wait, BABE. That's a funny word. So that became the name of the algorithm. Anyway, so here's some audio data with with nothing. This is the spectrogram, and you can see there's almost nothing above about 4 kilohertz. And here is the diffusion process. So you can see, or reverse diffusion process actually. You can see that we start from a big value of tau and count down, and less noise appears in the signal. We're actually using so-called stochastic sampling, so we actually have a different noise process in the added to the signal every time, but the neural network also learns to get rid of the noise. And down here we have always the best current best version of the underlying signal, and that's based on the statistics of lots of audio material that we have trained for the neural network. So it doesn't actually have to rely on that actual image over there, but it actually, based on its other knowledge, it knows what might be a good solution. And you can see that it actually fills the sky isn't so black anymore, but there are some events there. And this is actually piano music. We tested this with piano music and orchestral music. I'll play you this example. So here's the original. So it's a little bit dark. It's a little bit like somebody playing the piano, not here, but in the next door room somewhere. But now here is the clean or the reconstructed version, which has some more high frequencies. Especially the fortissimo part, you find that there's more high frequency, and it doesn't distort. So that's the great thing. We tried this also with other methods, but often the distortion kind of, if you add some high frequencies, kind of just try something, it sounds horrible. It sounds like distorted, like the piano needs fixing basically. So this works actually pretty well. All right. The next thing we also tried is so-called audio inpainting. So inpainting is this process where you have, I guess it comes from fixing of old paintings, like if you have an old painting that has some like a hole, for example, or something like that, and you have to fix it. So what they would do, they would somehow fill that hole and then paint it so that it fits the rest of the painting. And inpainting is this idea. And for audio, you do basically the same. If you have gaps in music, for example, such large like disturbances that there's nothing left of the actual music, you would have to take out the disturbance, and then there's nothing. And then you would have to find out what to do with that, well, to put there. And so we tried now a different diffusion model. This is, we use the so-called constant Q transform. In it's not exactly the same as spectrogram, but it's another type of spectral representation. And now we train it with 330 classical music pieces from the MusicNet dataset. And these are classical pieces of music and piano music and orchestral music actually. So, and here in this case we have 200 millisecond gaps. That's not very much, but that's, I think, very, very hard. There's, yeah, I think with traditional techniques and even other recent techniques, you can't completely fix that at all. Let's hear the original signal. It's here, so this has the gaps. That's quite annoying. So it lacks something. And now we tried several different techniques. So this technique is called ASPAIN-L. That was just introduced a few years ago. It uses so-called dictionary learning and sparsity. It's a pretty good method, but maybe not for such long gaps. It can fix shorter gaps. Where did I lose my mouse? There. And we can see here that it does something, but there's these fade outs still. Not clicks, but fade outs. Then we use something very old-fashioned, LPC, linear predictive coding. This is a technique that actually was used in the CDs, because the CD, although it seems like a perfect method to store music, and I guess many people think so, but if you have any like fingerprints or chocolate or some scratches in it, there will be mistakes. The laser is not going to find all the zeros and ones from the disk. There will be a lot of errors, and I think there's other techniques to detect and correct errors, but this is the final thing they do. If nothing else works, they actually extrapolate or interpolate from the existing signal, this kind of like stationary model, And this can hide clicks. Otherwise, the CD, maybe you've heard it, but it starts making these click, 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 click sounds, which are quite annoying. But this was used by Philips to fix those mistakes. And so it basically starts from each side of the gap and makes an extrapolation based on the waveform just there. And we'll hear how that works. If I find my mouse again. Maybe a little bit better, but you can see here that it kind of expands some of the notes, because all it can do is just like expand or continue what there already is. And finally, this is our technique, CQT diff plus. That doesn't have a nice name yet. That's a complex name, but here it is. Yeah, so it's a little bit better. It kind of hallucinates something, but it actually doesn't leave the gaps anymore, but it fills it with some like a statistically plausible material. And yeah, so it's not perfect, but it's there. So now we can get good or fair quality, so better than before. And here's maybe, if you still want to hear, this is the original, maybe you know the song. Anybody? Yeah. We can also try something more difficult. Long gaps. These are horrible things. These are currently impossible to automatically correct. And I can tell you, even this method is not really doing it, but it's kind of fun to see what it does. So now we have to rely on hallucinations. Generative deep learning techniques can hallucinate. Maybe you've seen these examples where you show a painting to the system and then ask it to, for example, expand it. So what's around, what's not shown in the picture. And we've seen these in the internet, some of these crazy versions of famous paintings where you can actually see what other stuff you could see in the background, perhaps. And so this is it. So now I had 200 hours of piano music, and now we have three seconds missing in the middle of the song. So let's hear that. So this is the original. I think it's again Bach. Oh no, this is the original. Yeah, there's no gaps here. Yeah, the next one has the gaps. The gap. So how would you guess what's missing? Well, let's hear. Let's see. Well, of course, we hope nobody would notice, but well, it's kind of easy to notice after all. Maybe if you didn't know the piece. Here's another one. I think it's Chopin. Ooh, in 3 seconds, how many notes can you play? Oh. No, now they're missing. There. All right. So let's hear what the deep neural network will invent there. Yeah, actually not so bad. Let's say if you didn't know the song and if that was playing like in a grocery store or in an elevator, maybe some people might not notice, but of course you have to be like accept it that this is not going so well yet. But basically because the neural network knows so much piano music, it actually plays piano music even with a very similar timbre and kind of similar style, at least a little bit, maybe not keeping the rhythm exactly and so on. But so that's the way. And of course, we can believe that in the future this should work. Somebody will find a way how to tame the neural network to actually understand about the beat of music and maybe the keys and all that. So and of course maybe in the long run, let's say it should be possible for AI to learn all music in the world, for example, and recognize the piece and the player and actually play it exactly the same way as in the record, for example, and maybe even find that recording from elsewhere and copy that segment from there. Okay, who knows? But so this just shows how where we are going just now. But in the future, of course, things will be better, and maybe quite soon. Who knows? Here's also the QR code if you want to try to see. We actually have quite a lot of examples. This is related to another conference paper where we did these different audio inverse problems, and there's also other things, including I think declipping and sparse sampling or something like that. Anyway, let's go to another topic. So I showed you examples where we can train a neural network to solve different audio problems which we thought were really hard or impossible, but because there's been a way to have training data, paired training data, good stuff and bad stuff that you can compare. It's kind of possible. But what if there's no? And I know a problem where that happens. Audio timescale modification. It's this idea of if you have a short recording, what if it's in a soundtrack of video, somebody wants to make a slow motion version of the video and wants to slow down the sound? Where could you find training data for that? If you have a good idea, let me know. We haven't found a way to do that actually so far. That's actually an impossible problem kind of, but of course engineers will solve anything, and of course we kind of try to solve it, and people have been trying to solve it for years. In many digital audio workstations there are systems that solutions to do this in one way or the other. So yeah, just last year we actually tried also to use a neural network for this. So we have a system that's based on decomposing the sound into sines, transient, and noise, so different types of sound components, and then using a neural network to play the noise part of the sound. That's a wavenet synthesizer. Also, Alec was also involved in this research actually. And so we basically, the system wavenet can basically play the noise at different frame rates, and that way kind of do exactly what we wanted. And it actually sounded sometimes quite good. Sometimes it also hallucinates, so sometimes it just makes some rubbish, and so we had to generate many versions and pick the one that sounded the least disturbing sometimes. But anyway, it was kind of working. But in the end, just after that, we discovered, we had a little project about this, and we discovered a technique that can actually do it much better. This is called noise morphing, and this is not neural network. This is just kind of traditional DSP. So what we do here is we have the separated noise part of the signal, let's say that yellow signal over there. And if we want to stretch it by factor 3, for example, we first generate this green signal here, which is white noise. And we actually do spectral estimation, like spectral shape estimation in short frames from the original signal, and then we multiply or overlay them to this white noise. And we can then separate the frames, and we can actually make a version of the stretched version of that noise that sounds really, really good. And the secret here is that because it's all based on this same white noise, although it's a random phase signal, there's some continuity in it. And when you do this, it actually sounds quite nice. Previously, there was always some artifacts when you did that, at least with a big factor. But now it's actually pretty good. This was also published earlier this year in the IEEE signal processing letters. There's a link also if you want to see how it goes. And so here's some examples. So this is a short sound effect. It's I think opening of a soda bottle. No, not that. Let's see, where is it? Here. Exactly, you heard it twice there, but anyway, that's it. And so here is a version of 3 times such version of that when we didn't actually separate noises and transients, but we just do them at one go. it sounds pretty nice, but actually some of the sharp events are, or kind of percussive events are not there, and so it didn't work so well. But when we do the separation of for transients and noises and use the noise technique, noise morphing technique for the noise, it actually sounds really, really good. This is it. So you heard some of these metallic noises were still quite sharp. And this is also the version that the new WaveNet does, which actually in this case is also pretty good. Maybe not exactly the same, as good as the noise morphing technique, but pretty good. Let's see where it is. Yeah. But in other cases, we found that indeed the noise morphing technique actually beats the neural network, and of course that's kind of entertaining. So here's an original sample of music, some electronic pop music. Okay, now we are going to expand this by factor 2. And the anchor sound here is a classical phase vocoder, but I think we might have skipped some of the sophisticated things. I think this is the worst ever phase vocoder sound example because it really has all the artifacts there can be. But this was used as an anchor in this study actually. Yeah, I also played this in the conference. Somebody said, "How could the phase vocoder sound so bad? I've never ever heard such a bad phase vocoder in my life." But well, that's it. But here's the WaveNet. Much better. And this is the noise morphing technique, which also is pretty good. Yeah, but okay, factor 2, that's not extreme. How about factor 8? Let's see. And now the phase vocoder is really suffering. Yeah, pretty much anything you throw in will sound like a proper airplane or something like that. But the WaveNet is still going strong. And I think you would have to pay attention to the snare drum sound. I think that's where you hear some of the artifacts here. So very slow. Yeah, but I guess, yeah, in slow motion video, things might get really slow. Yeah, but it sounded pretty good. But there's something in the drum, I think, that people notice. There's a little bit of like fluttery sound there. But this is the noise morphing technique. Yeah. So that's so far the best methods we have found for doing time stretching, and I think many people find that this, whatever you heard last, is actually a pretty good approximation of how that original pop music sample could sound when you stretch it by factor 8. Of course, we don't really know how it should be, so because it doesn't exist, but people usually, at least when we give these to as like test items to them in a listening test, they actually quite soon figure out what's good and what's bad there. So it turns out that we have this kind of mental idea of how sound could be stretched, although in reality, of course, we can't really do it. Okay, but so this is an example where signal processing wins over deep learning, and I think we were so happy when this happened. Okay, and this actually concludes my talk now. So yeah, so I showed you that deep learning can solve many digital audio effects problems, and often actually expectations are exceeded. So it is so good. They say that deep learning can do miracles, and it's true. It really can do miracles. I've been so much surprised many times. But if there's this case where there's no training data, you're in trouble with machine learning. You have to get that training data from somewhere. You have to play it yourself, or ask some friends to play it, or somebody. You have to get it from somewhere. If you can't, then something else like or traditional DSP might win. Yeah, and also I would like to tell to everybody of you, also each one of you, that these signal processing skills are still useful, and they are actually fully compatible with these machine learning techniques. It's all digital anyway, especially in pre-processing and those loss functions or error computing, and in spectral analysis. You can use all the tricks in the world from signal processing. So don't forget about that. So because I know there's already so many like machine learning engineers who are kind of doing all this, but they have no clue of signal processing anymore. They only know about machine learning, and I think that's a mistake. They shouldn't do that. All right, and here are some of the references, some of our papers, and some of those like the first DAF. This concludes my talk. Thanks so much. Right.
Any questions?
Yeah.
Do we really have no questions?
No
It was
questions.
very clear.
Ah, there's one.
Okay, yeah.
Go ahead.
Thanks. People can.
Oh yeah.
It's just a microphone.
It's actually a Finnish microphone.
Yeah, I think in the first several pages there is a weighting filter, and I think that there is a boost in the mid-range frequency, right?
Yeah.
Yeah, because it should be 0 dB at 1 kHz.
Yeah.
So yeah, I see some boost there. So is it because you're using a guitar, and so you are trying to get a filter that can better filter the guitar sound?
Well, I think the low pass, like the attenuation at very high frequencies, maybe is because we are dealing with guitar signals, because we already know that there's nothing much there, so the training should not concentrate that on the high frequencies at all. But I think the rest of this curve is actually really based on the properties of hearing. So we are not very, the hearing system is not very sensitive to low frequency sound below like 500 Hz or so. We hear it, but we are not so sensitive as we are in the 1 to 3 or 1 to 5 kilohertz region. This is actually based on the properties of the outer ear and the ear canal, which has a resonance there. So it's probably originally because we want to hear human speech and human sounds very well. So that's why this happens to be so in the human hearing mechanism. But we are just imitating the way people hear sounds, basically.
Yeah, so this one is filtered to cater their human hearing, or just it's because you are using the guitar sound? Because I always hear the guitar.
I would say that this, from here to about there, it's because we are doing this for humans. This thing is because we know that in guitars there's nothing there anyway.
Okay.
A little bit of both, but mostly because of the human hearing system.
Yeah, and I have another question is that is it more useful to calculate in the frequency domain? Because I saw a lot of SDFT there. So
yeah.
What's the difference between?
Yeah. So in this case, all the computing was done in time domain. So it was better to do it in the time domain. So we actually figured out what is a filter response that does this. We actually used a convolution, like an FR filter, to implement this. Although there might be better ways in signal processing, but for the machine learning technique, it can do very easily big convolutions. So this was a very easy thing to do in the pipeline, the training pipeline. So it was done in the time domain. But of course, now if you're doing like things in the frequency domain fully, then you could do the same, of course, in the frequency domain, like multiply your signals with this, for sure.
So in this chart, it's not 0 dB in one case. So
yeah, well, you know, it actually It doesn't really matter, because it just matters where you have bigger gain and lower gain. It's all just meaningless numbers in the end inside the machine learning technique. It doesn't.
Okay.
You can change the scale here. It's just that you want to make this difference between important and less important areas.
Maybe it gives you saying RMS or something like this.
Well,
it makes sense that it goes above.
Yeah, it makes sense. Yeah, but I guess as long as you're not like exceeding the numerical range of the computer, I guess you're okay. So, of course, I wouldn't like put everything to very low gain either. But like I think the details here don't really matter, I would say.
Yeah.
What does Alex say? Alex knows better.
I agree with you.
Yeah, thank you so much, Alex. Yeah. Scaling is kind of meaningless here. Yeah.
Thank you. So in terms of the sound that you produce with your systems, have you a good reference system that you use for the playback of that? And have you noticed any limitations, maybe when you move into sort of higher end sound systems, maybe things like live sound, where there is more focus on the lower frequencies, particular types of music, for example?
Yeah, that's a very good question. So it turns out that most of the times, and also in all these cases that we are showing here, we had to do all these subjective tests with headphones. That's just the way it is. If you want to publish your work in a good conference or journal, you just have to use headphones. If you have a playback system or something else like a PA system and you have a very sophisticated systems, whatever, they would say that was this done in a silent room? Was the background noise the same for all listeners? Were there any random noises, or what about the location of the listeners towards could they move their head and things like that? It's an endless flow of questions, and finally the only thing you can do is put them the listeners the same headphones or same type of headphones. Usually we use always the same German good headphones, which maybe I don't advertise here, and we put them in booths that are like sound sealed, because that's the way. Then you can say that it was in a silent room and the same headphones and good headphones were used, and that's it. And then you're okay to go to science journals. But of course, I'm with you there that, like, of course, finally we should use like test these with like maybe rock musicians on stage and everywhere. But that's a little bit different thing. For science, you just can't, because if they can move, for example, that's no. You can't allow them to do that. And if there's extra noises, like somebody drumming at the same time, no, and so on. So that's it.
So at the complete opposite end of the spectrum, have you tried things like prosthetic skulls with the headphones, or is it always a human listener? And it's
we have to. Yeah. So far there is no. We also have tried to use like objective measure. So there's techniques to measure, for example, the differences between these different signals and evaluate like how this might sound for humans. Like kind of predict these quality categories, but it's very unreliable. It's very unreliable. It really only works for kind of certain audio codecs, because these techniques were really designed to make differences and find differences between audio codecs like MP3 and AAC and things like that. So there they have some value, but here we've tried some of, and it's usually quite random. Yeah, unfortunately. So human listeners so far are very precious. They are our kind of meters in this work.
Thank you.
Thank you. Good questions. Yeah. Yeah. Maybe please wait for the mic.
Oh.
No worries.
And can inpainting be used to improve overload distortion? Inpainting.
Overload. Yeah, I guess
yeah.
you could. Yeah. If you have a clip signal, yeah, you could use it for that as well. Yeah. You could. Yeah. So it's basically one of these cases where if you have kind of a distortion or like disturbance that you can't otherwise like fix, you just take it out and you leave zeros there, and then yes, you could do it with inpainting. But yeah, let's say yeah. But then if you know that it's overloading, yeah, it might be actually easier in the end to do it with a technique that actually it's a declipping technique that knows that the signal, that's the minimum level, so it has to be over it, because otherwise I guess the inpainting technique just doesn't make assumptions like that. It might replace the gap with signal that has any values, which might not be okay because you know already that it has to be over.
Okay,
But otherwise they are very similar. So we actually use very similar techniques for inpainting and declipping indeed. Yeah. But yeah, you could. Yeah, good point. There's another one. Maybe we can try throwing the microphone to the next one. Yeah. I think that's the only idea of that you could actually throw it. It's yeah. Yeah.
So you showed off one of sort of this stretching algorithm that was DSP based. Have you tried training data with that and then using a neural net to extend that?
Yeah, that's a brilliant idea actually. Yeah, we haven't done it yet, but yeah, that's true. This is something that can be done. So if you have another algorithm, no matter how complex, you could basically produce training data yourself and replace all that computing with a neural network. In some other cases, we've done something like that, but not here. But yeah, this might be something we could do later.
Is it faster to do something like that, or?
So it depends, but it might be. But like, yeah, it might be actually, yeah, because in that case, where the examples I showed you, let's see, where are they? So here, like, what we actually had to do, we had to, where is it? Where it is it? So what we actually do, we kind of separate these, we compute the spectrogram and we separate like the sine wave components and the noisy parts and transients, and we handle them separately and then put them together. And now let's assume that the neural network only saw the input and the output. It would not ever have to even know about the decomposition. So yeah, there's a chance that it might be simpler because it would basically just see some like samples going in, samples going out, and it would just make a direct kind of nonlinear mapping between the two without knowing how much complexity there is. And if it might find that it's not that complex after all, that we are overthinking it when we do all this decomposition and everything, which requires lots of FFTs and stuff. Yeah, there's a chance that it might, but I haven't tried, so it's a good idea. You can maybe try, or somebody else. Yeah.
Right. For the like denoising algorithm, how does that work with kind of more transient sounds? Does it work just as well if it's removing like clicks and pops as well?
Oh, that's a great question again. So I think this time we haven't really tried, but there's a few classical music recordings that you really should try. There's is it 1812 overture that has some, I think they use a whip with the symphony orchestra. These whip sounds, at least back in the day when we did this like detection of clicks, often the clicking detector actually would found these whip sounds and would remove them because they sound like like extra stuff, not like orchestral music. Like actually we didn't try. We should still try that one. Yeah, there might be other examples. It maybe yeah. But of course, this was only trained for classical music so far. So, of course, if you play some electronic music, for example, it would certainly do harm because it doesn't know about it. So it would remove, I guess, any electronic sounds probably. Yeah, but that's a good idea actually. Yeah. Good, really good question there. Yeah. Of course, if you trained it with electronic music, then it wouldn't remove all the electronic sounds anymore, maybe.
So that's it.
Yeah.
No more questions? Then yeah, we just have to say thanks a lot, Vesa, and thanks everyone for coming.
Yeah, thanks for coming.